Here is an example for Lorenz. As you will discover, Poincaré sections are dark art, partially aesthetic, partially some intuition about the flow. There are sort of some thumb rules how you should construct them, but it's not obvious ever when you work in a particular system. So here I'll give two examples of section that might make sense to you. One of them is a Lorenz flow, as you remember, was a flow in which there was some motion like this, and then every so often that motion flips on the other side. So a section, the motion is around the equilibrium point, as we showed last time. So a natural way to choose hyperplane is to make sure that it goes through equilibria. In this way, at least neighborhoods of equilibria will be nicely cut. And in this particular case, it's convenient to make the plane, in this case, not some curved hypersurface, just a plane. It's convenient to make it such that the section goes through the z-axis. It'll turn out that's an invariant axis of the symmetry of this problem. And so we have a surface. And now what this surface does, it cuts in oriented way the flow. So what you see here is you see bits of the flow which are toward us, and they're made gray. They are made gray whenever they get behind the plane, and then they do their thing. They come out or jump down, and then they come out here, etc. And as a result, you have a bunch of points which are oriented crossings. Now, pretty soon you realize there is no point of doing this twice because of the symmetry. It's good enough to just take half of the hyperplane. That's indicated here. So this is our first Poincaré section P. And now when we look at the crossing, you see the flow looks much simpler. It's just a smooth line with dots lying on a line, as far as we can tell. Or you might say, well, this is not so interesting to me because I would like to understand jumps. This one was focused on equilibria. This Poincaré section had to do with equilibria. Equilibrium. So let me take another Poincaré section. This is P1. Which keeps track of how I jump from this side to the other side. So this is our Poincaré section P2, and I've later here on the side, or actually Evangelos Siminos who drew this picture. And this, is a different section of the flow, but topologically looks similar. So that's a very simple example of a Poincaré section, and I hope you will implement this by doing the problem set. Another example which we'll often use in this course is the example of Rössler strange attractor. And in that case, we'll do the same as I just showed you in Lorenz. So what we'll do is we will take a plane, half plane, that goes through here, goes through this equilibrium point, and the section of the flow is this line, for example. So this is our Poincaré section A. So you can visualize this plane here, tuk, 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 tuk. And this is where the flow pierces it going through. It looks rather boring, but okay. You'll find out that that's actually extremely good Poincaré section. Now you have a great deal of choice how you do the sections. So let's turn it by 90 degrees, and that will be this other section here that you see. Didn't want to do that. This other section, let's call it Poincaré section B, so hyperplane going at 90 degrees away from us. This is kind of interesting what has happened to the flow. This line has stretched and become bigger. Then we turn our plane by another 45 degrees or so. That's the plane C, this one. And, you know, when we look at it, the thing has started folding. Then we go to the plane, this one, Poincare section D, this one. An interesting thing happens, the thing gets pinched, and unfortunately the scale is gone from this figure. It should be on the right-hand side. It turns out that as we go further, this gets very, very thin in the units of this figure, which was of order 20. This gets to be very small. And by the time we get back, we'll find out that the thickness of this is 10 to the minus 14. I'll explain why. And to see the orientations of the section, we also gave you another picture from above, this picture here. So what we learned from this is the essence of chaos from this very simple example, and that's why Rössler designed a simple example. What we learned is that the line segment, AB, so this line segment, which starts close to the xy plane in the beginning, it gets stretched and folded, so it does something like that. So we find out that flow is locally expanding. But then this folding is followed by being bent, and so here you're being bent, and then you're being scrunched down here. In this one, bent, and then you're being pushed down into the plane again. So the thing that used to be a straight line has been folded onto itself. And there are three kinds of points on this straight line. There are two edges. So these two edges, let's call them A and B. A and B, A and B. What happens now, A lands here and B lands there. And once you're done, you realize there's another point, which we'll call turn back. Turn back C. And this one becomes the new edge. So what used to be B is now the new edge. So the flow is stretching, and then it's mixing, because what used to be on the edge is now plump in the middle of the thing. And what chaos does is it takes that interval, folds it onto itself, does it again, folds it onto itself. Mathematicians like to call this kneading. It's a very natural operation that you do in doing Danish pastry. For example, I did it on a science program for Danish television. I went to Danish baker Iverson, and we did Danish pastry in the same mixing. And what you find out, if you do some estimates, after maybe 12 of this mixing, the things are already mixed on levels of molecules. So if you had something that was white and red in the beginning, you get pink dough very quickly. So kneading is very effective. So that's what chaos does. Nearby things separate, and far away things actually get very close by ergodic motions on a strange attractor.